Kirchhoff's loop rule, and then the overall V equals I times R equation in order to actually analyze this entire circuit and find the voltage across each of the resistors, the current at I1, I2, I3. Yeah, so let's begin. So when taking a quick look at this overall circuit, we notice that we have a capacitor here, battery here, battery here, battery here. Batteries in red, capacitor in yellow. Since that's the case, we know that after a while, capacitor will actually become fully charged, which will cut off the overall current. So we know that from here to here, there is actually no current. Since the capacitor has been running, since the circuit's been running for a while and the capacitor is fully charged, we know that what I have highlighted in red, there is no current flowing through those wires. So with that being said, we don't have to really worry about this portion of the circuit. Since there is no current there, it's not going to be very helpful in actually figuring out what's going on in this actual overall circuit. So what we're most interested in is the circuit I'm highlighting in red right now. So this circuit is what we're most interested in. Now the equations we're going to be utilizing in order to solve for this circuit is going to be delta V equals 0, V equals I times R, Ix plus Iy equals Iz. Now with these equations, we'll actually be able to solve for just about everything on this circuit. And I'll show you how by utilizing matrices. And I'll also show you how once you actually use the matrix to go back and algebraically prove that everything is what it is on the overall circuit. So let's start by writing some equations out. So the first loop we're going to actually look at is the loop I highlighted in red. So V2 is actually already given to us as 9.3 volts. So 9.3 volts is where we're going to start at. That is positive because we are going from lower potential to higher potential. So let's now go on to the next step. Let's find our next resistor. We are now at our next resistor. We are actually going in the opposite direction of the current, so that will be once again positive. So we will have positive 3 ohms times I2. Let's look for our next resistor. Next resistor right here. So our next resistor, we have I1 going across that. So since it is going in the same direction as the current, it will be negative 5 ohms times I1. Now we have to set this equal to 0 because Kirchhoff's loop rule states that the sum of all the voltages must equal 0. This is equation 1. Let's make another equation real quick. Let's take a look here. So I will highlight our next loop in yellow. Here we go. So this is actually already given to us. V1 is 6 volts. Starting at I3 though up here, we are going in the same direction as I3. So that would be negative 5 ohms times I3. And then that would be plus 6 volts. Then we are going in the same direction this time as I2 right here. As you can see, we're actually going in the same direction. So that would then be minus 3 ohms times I2. And that's actually going to give us 0 again. Now there is one, you could do one overall giant loop. But for this case, we're not going to do that. We're actually going to do Kirchhoff's junction rule, which states what comes in must go out. So that would be I1 plus I2 equals I3. And that is right here. We have I1 and I2 going into node C, and I3 is coming out. So, with these equations, we can actually set up a system of equations and solve it via matrices. How do we do that? So, step one, you're actually going to want to get all the like terms combined. So looking at this, we don't have any like terms we can combine. Step one, I'll write here, combine like. Step two, we want to get the voltage over to the right side of the equation, just leaving us with the actual currents on the left side. So for the first part, we will actually subtract 9.3 volts over to the left side. That will then give us negative 9.3 volts on the left side, since we got rid of it on the right side. That will then give us this. Looking at the second equation, we have 6 volts. We would have to subtract that over to the left side, which would then give us negative 6 volts on the right side. So now that we have all that step 1 and step 2 done, we can move on to step 3. Let me just write this out real quick though. Okay. Step 3, looking at the junction rule. The currents that are positive will remain 1. So I1 plus I2 equals I3. So we replace I1 with a 1, positive 1. We replace I2 with another positive 1. And now then we would then subtract I3 over as a negative 1, minus 1. And then we would set that equal to 0. And you just have to rewrite it like this. It doesn't make sense algebraically, but in order to enter it into the calculator, this is how you write it. So since I1 plus I2 equals I3, but I3 is on the right side, we would have to subtract I3 over. And since we don't actually know the currents yet, so the calculator doesn't get confused, we just label them as 1s. So we're subtracting I3 over to get it over to the left side, and we're keeping I1 and I2 positive. And then we're just setting that equal to 0. And I'll show you on a matrix what this will actually look like. So now we actually have our 3 equations. Now we can actually construct a matrix. So when we look at this, your I1 values will go here, I2 values here, I3 values here, voltage here. So looking at the first equation, let's find I1. I1 is the number in front of it is what you want to actually insert into your matrix, which is negative 5. So we have, I'll put I1 in red, my bad. Negative 5. Now let's see what we have for I2. Look at the number in front of I2. That is positive 3. So in the calculator, I will write this in blue as positive 3. Now, if you don't have a value in your equations for I1, I2, or I3, you label it as 0 in the matrix. So this I3, since it's not in equation 1, will be labeled as 0. For the voltage, of course, that is just negative 9.3. Moving on to the second equation. Once again, find I1. There is no I1, So that then is 0. For I2, what do we have for I2? Looking for I2, negative 3. So we then put negative 3 as our I2 value in the matrix. I3, let's see if we have I3 on here. We look at the number in the front. That is negative 5. So then for I3, we would put negative 5. And then, of course, voltage, we have negative 6. The final one is just right across 1, 1, negative 1, 0. So your overall matrix should look like this if you actually match it up properly with your equations you set up. So double check your equations, double check your matrices, and this is what we will actually end up inserting into our overall calculator. Now I'm going to show you how to do this. Let me just copy and paste this real quick so when we go to the next step, I can show you how. A blank page. Here's where the fun begins though. We're going to actually insert it into the calculator. So step 1, turn on your calculator, and then step 2, click second, then this button right here, which will bring you to the matrix screen. Once you're on the matrix screen, it should look like this. You're going to want to scroll over and click edit on whatever matrix you actually want to edit. But remember what matrix you're editing, because that's the matrix you're going to have to actually insert into the final portion of the calculation. So if you edit A, make sure you put A in at the final step of this process. Click on any matrix to edit. Once again, I chose A, so I clicked A. Once you get to this screen, we want to create this matrix right here on our calculator. So by looking at this, it's going to ask you what by what you actually want the matrix to be. So we have 1, 2, 3, 4 columns, and we have three rows. So we would want to do a 3 by 4 matrix, because once again, three rows and 4 columns. So 3 by 4. Of course, I entered that in right here when it asked for it. That would then give us a matrix with a bunch of random zeros on it. And then once again, you're just going to go to each of those and insert these values that we have. So you would start there, you'd put negative 5, then it's going to bring you over 1 to the right, 3, 0, negative 9.3, 0, negative 3, negative 5, negative 6, 1, 1, negative 1, 0, until you're completely done entering all the values into the matrix. Once you do that, you should have the overall matrix in your calculator that looks like this right here. Click second and quit. Where's quit again on the calculator? Second quit, and that'll bring you back to the main menu. Once you're at the main menu, hit second matrix again. It'll bring you back to the matrix menu we were at originally. However, instead of going over to edit this time, you're going to want to go over to math. When you're at math, click RREF. When you click RREF, it'll bring you back to the main menu, and you should have something that looks like this. Now, when you have RREF on the main menu, click second, then matrix again, and that'll bring you to the matrix menu. Rather than scrolling over to edit or math, you'll just stay at names and you'll click enter on any of the matrices you actually want to insert into RREF. Since we actually used A to construct our matrix, you would click on A, click enter, and then A should come up right here on RREF. Just like this. Now then click enter and watch the magic begin. So, how do we actually analyze this? So we know that these values right here is what you actually want to know if you did it correctly. There should be ones that are diagonal. If the ones are diagonal like this, that means you actually constructed the matrix correctly and you actually constructed the equations correctly. The right side are the values we actually are concerned about, because these are our actual currents at each spot. The first one, right here, is I1. The second one is I2, and the third one is I3. So I1 equals 1.68, I2 equals negative 0.3, I3 equals 1.38. Now then, why is it actually negative for I2? It's negative because the direction we have drawn on our circuit is actually incorrect, and that means that the circuit is actually going in the opposite direction. So in reality, you really can't have a negative current. The actual current is just 0.3. When it's negative, that just means the direction we drew it in on our circuit is incorrect, and it's actually going in the opposite direction, which I will show you. So let me copy and paste this, and then we're going to algebraically solve for everything on this circuit. Copy. Let's go back to the overall circuit. Here we go. Okay, so I'm going to erase all this because we don't need this anymore. Once again, we had these as our currents. So, since it's negative at I2, that actually means that the direction of the current is actually flowing in this direction. It's not actually flowing upwards. It's drawn incorrectly on the graph. However, you can still get the same equations and stuff as long as you just follow Kirchhoff's junction rule or loop rule properly. You'll still be able to get all the same equations and the same values. But when it comes up negative 0.3 amps in the overall matrix, just remember on an exam it would still be 0.3. And if they ask why was it negative that you actually were able to calculate, you would say that the direction indicated on the overall circuit was going in the incorrect direction that's actually occurring on the circuit in real time. So, we now know that's 0.3. Now that we have all of the currents figured out, we can actually go through each resistor and figure out what the actual current or what the actual voltage is at each of the resistors. So let's start with this resistor right here, the one with I2. We know that V equals I times R will give us the current and the resistance and the voltage, as long as we have two variables. So resistor CF, we'll call it, the voltage of resistor CF is equal to 3 ohms times I2, which is 0.3, which is then going to give us, let me see my calculator, 0.9 voltage. So the voltage at this resistor here is actually 0.9 volts. Looking at the resistor FG right here, so voltage of FG, that would equal 5 times I1. I1 is 1.68, which then gives us 8.4 voltage. .4 voltage. Now looking at the final one, which is, we solve for FC, we solve for FG. We now want to solve for CD, which is right here. We would do V of CD equals 5 times 1.38, and that's then going to give you 5 times 1.38, 6.9 voltage. So this is 6.9 voltage. So we have now solved for the voltage and the current at every spot on this graph, or in this circuit. So there's a problem on the practice exam that says if we know 1.68 is going through I1, which we actually already solved just by looking at those equations, how can we prove this? Well, you could show all those equations and then do this. So now that we know the voltage across each of these batteries, we could prove that 1.68 amps is going through 9.3 volts because we could actually show Kirchhoff's junction rule, which would be the overall loop. So now we can actually draw an equation for the overall loop like this, and I will show you how we do this. So we have 9.3 volts, and then we have minus 6.9 volts, and then we have plus 6 volts, and then we have minus 8.4 volts, and that should equal 0. So first step is just to check and make sure we did everything correct. This should equal 0 if we got these voltages all correct. 9.3 minus 6.9 plus 6 minus 8.4 equals 0 if you do that in the calculator. So we did solve the voltage properly for all of those resistors and batteries. So once we have that, they now want us to prove that there is 1.6 amps going through V2. So how do we do that? Well, we already solved the voltage and the current for each of these positions. So now then what we want to do is we could make an equation like this. So let me think. We could do this. Could do. Let me see. So we know I3 and I2, so we could actually do this right here. We can do. Yeah, let's do this. So let's draw this equation. 9.3 plus I2, which is, we know what I2 is now, 0.3 times 3, and then we can then subtract that from I1, which we don't know what I1 is yet. 8.4, no wait, that's voltage, my bad. Then subtract that from 5 times I1, which is 1.6. Oh shit, no, we're solving for I1, I forgot. Because if we wanted to go back and actually solve for I1 without using matrices, I1 then equals 0. And then just solve algebraically, and you should be able to solve for I1 by using this loop right here, which I just used one of the old equations for. So let's do this real quick. 9.3 plus 0.3 times 3 gives me 10.2. And just double check. Minus 5 times I1 equals 0. And then if you do this, subtract 10.2 over, So then you would have negative 5 I1 equals negative 10.2. Do negative 10.2 divided by negative 5. No, I set that equation up wrong. I apologize. Because I forgot. Once again, I keep forgetting. I proved that he has it going in the wrong direction. So this would have to be negative. So this right here would then have to be negative 0.3. So 9.3 plus negative 0.3. Even though the actual current there is 0.3, we have to put in negative 0.3 because we're going in the opposite direction. So now then we would have negative 0.3 times 3. Negative 0.3 times 3 gives you negative 0.9. So this is negative 0.9. This is 9.3 plus negative 0.9. 9.3 plus negative 0.0 or negative 0.9. That would then give you 8.4 minus 5 times I1 equals 0. And then subtract 8.4 over. That would then give you then negative 8.4 divided by negative 5. And that will give you 1.68. And that is then how you could prove that there is 1.68 amps going through V2 after solving for everything on the overall circuit. So once again, recap. We were able to, via matrices, solve every single portion of this circuit. We found the voltage right here, voltage of this resistor, voltage of this resistor, voltage of this resistor, voltage of this resistor, and then we also were able to find the current of I1, the current of I2, and the current of I3. We were able to work backwards and prove that I1 was 1.68 by then just plugging in plugging in I2 into the equation. And then remember that I2, if this was ever on the exam, was actually incorrect in the incorrect direction because it said it was negative 0.3. So in reality, the actual direction of this current would be going in this direction at 0.3 amps. It would not be going in this direction. So that is a recap of everything. That's how you actually solve by using matrices, and that's how you solve at the end algebraically, plugging everything back in to prove that there is only 1.6 amps going through V2. Thank you very much, and I hope you guys have a wonderful day.